Hello everyone, welcome to the last sections uh, about about the velocity autocorrelation functions, and let's have a look of the questions here. So actually, here we want to introduce uh, what's the meaning of velocity autocorrelation functions. So actually, this is a mathematical tool for analyze the motion of molecular systems. Uh, So actually, because it's very nasty to look all the trajectory of of all atoms. So this velocity autocorrelation functions and give us a quick uh, give a shortcut to understand to characterize how all the atoms behaves. So actually we were going to look at the Fourier transform of this velocity autocorrelation functions to describe to understand what's the intrinsic property of the molecular systems. So in the part A, we want to introduce the Fourier transform. So I think the Fourier transform is nothing but just uh, to 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 read the signal in the frequency domain instead of time domain. And so here, this is a definition of a Fourier transform, which is the integral of these functions, which is a time dependent functions with the exponential I omega minus I omega t. And here we have the prefect of 1 of square root of 2 pi. And here this is the inverse Fourier transform, which is similar, just the integral with respect to exponential I omega t. And here this is something wrong. This should be d omega, not dt. Okay. So here we want here we have a very simple examples. So this is our a time domain signal, which is given by cosine pi t plus 2 cosine pi half t. And then we want to calculate analytically the Fourier transform of these functions. And here and we need to use a trick of this identity of this Dirac delta functions, which is given by the integral of this exponential omega 1 minus omega 2 t times dt. Okay, so the goal is trying to perform the Fourier transform of this one, and let's go back to the writing panel. Wait a second. Good. So here, this question is about the velocity autocorrelation functions. Or VAF. And in the part A, we want to perform the Fourier transform of these functions. With the help of this mathematical identity of the Kronecker delta functions. Good. So now we perform the Fourier transforms. So the trick to do this is to use to try to rewrite all of these cosine function in terms of the exponentials. So actually, we're going to use this formula. We're going to so this is what we need. So you will get this 1/2 exponential I pi t plus 1/2 exponential minus I pi t. And the 2 times 1/2 is 1, so we have a 1/2 pi I 1/2 I pi half t plus 1/2 exponential minus I pi half t. So this is our functions. And now we want to perform the Fourier transform on these functions. So this f means the Fourier transform. So the definition of Fourier transform is square root of 2 pi, 1 over square root of 2 pi, and integrate from minus infinity to plus infinity. And with the functions here, sorry, 1/2 exponential I by t plus I by t, so I pi half t, and the times exponential minus I omega t dt. Then you can combine all of these exponentials, which is very easy. So you have 1/2 exponential minus I omega minus pi plus t exponential minus I omega minus plus pi t. And you also have the other terms, exponential minus I omega minus pi over 2 t plus exponential minus I omega plus pi over 2 t dt. So now you can recognize these delta functions. You can compare this one. This is like, if you compare these delta functions, then you can immediately recognize this is nothing but 1/2 delta omega minus pi plus delta omega plus pi, and delta omega minus pi half plus delta omega plus pi half. So this is the Fourier transform of the function f of t. And if you try to plot this in the frequency domain, this is omega, and this is your f of t, f of f. You can see here is pi half, this is pi, this is pi minus pi half, this is minus pi. Then you can see it in plus or minus pi half, you have a strength of this delta function at 1. And so this arrow means strength because the delta function is infinity anyway here. So it's only meaningful to talking about the strength, which is the strength means the integral of the delta functions. And on the other hand, for at omega equal to plus or minus pi, the strength is 1/2. This is 1, and this is a 1/2. So this is our result in Fourier transform. Okay, so this will end the section part A. Now let's go back to part B, and let's open the question list again. So here in part B, we will define the velocity autocorrelation functions and its Fourier transforms. So actually, the velocity autocorrelation function is defined here as the integral of these cross correlations of function f and g. So this is the definition in the probability theory, and yes, we want to apply these to these correlation functions to the velocity, which we have already solved from the exercise 2.1 from the molecular dimer in the interpretable result. So actually, what we want to do is try to calculate the velocity autocorrelation functions for the molecular dimer. Okay, so let's go back again here. Let's go back to the writing panel. So here, let's rewrite this velocity autocorrelation functions. So this is by definition is equal to the integral from minus infinity to plus infinity of the velocity v of tau, and with a time delayed v of t plus tau. The integral with respect to d tau. So actually, this definition is in the probability theory. But now, actually, in statistical mechanics or condensed matter physics, statistical mechanics, the definition of this velocity autocorrelation function is slightly different. So actually, the velocity autocorrelation functions is given by the limit of t approach to plus infinity. Sorry. So actually, it's actually the time average of this integral. The argument, the integrand is the same. And the only thing different is now we take the average instead of the whole integral. So this bracket this bracket is means we take the average of this velocity correlation. Okay, so actually we will use these definitions instead of the first one. So now we already have the definition of this velocity autocorrelation function, right? And now the next thing is we need to what's the velocity? So from time in the front on the sections part A for the sections 2.1 we already know that the velocity is nothing but minus omega x hat and sine omega t. Okay, because we will apply the Fourier transform to these velocity autocorrelation functions. So to avoid the two to avoid two identical parameter, we will distinguish the frequencies here as omega 0 because we have another omega for the Fourier transform, but these two are different. So now we have, and don't forget this omega 0 is nothing but square root of k over mu. And if you apply this, if you apply the harmonic approximation for the Morse potential, this k is nothing but 2 dB squared. Good. So now what we need to do is to plug this v of t into the velocity autocorrelation functions. So v af of t is nothing but so we can take off this omega 0. So here we have v of tau and the vt plus tau. And this prefect we can take out from the integral. And now we have this limit t from approach to positive infinity minus t half to t half. And here we have sine omega 0 tau times sine omega 0 t plus tau d tau. So we need to integrate this combined this product of these sine functions. So actually, to this we need some mathematical tricks. So if you remember in high school, maybe you remember these tricks. So actually, we have this identity -2 sine x sine y is equal to cosine x plus y minus cosine x minus y. So you can identify the x and y in the plugin and use these expressions. So this sine, so this sine omega 0 tau sine omega 0 t plus tau is nothing but 1/2 cosine x minus y. So this would be t plus tau minus tau. This will be tau minus t plus tau. This will be minus tau. Minus tau omega t minus. And don't forget the cosine minus omega t is the same as cosine omega t because this is an even function. And then the other one is cosine x plus y. So this will give you cosine omega 0 t plus 2 tau. So now we have to integrate with respect to tau. Then you can get this of this prefactor is still here. So we integrate, then the first term is not depending on the tau. So this will give you tau, right? And we can put this 1/2 to here. So we have cosine omega t times tau minus, but now this cosine is the second cosine is depending on tau. So this will give you 2 omega over 1 over 2 omega sine omega 0 t plus 2 tau. And the upper bound is t half. The lower bound is minus t half. So actually this term will become 1 over t. Okay, maybe I will write everything here again. So we have limits t approaches to plus infinity or 1 over t. And then here we have t half minus t half. So this will be t. So we have cosine omega 0 t times t. Right? And here we have 1 over 2 omega 0. And then now this will give you sine omega 0 t plus t minus sine omega 0 t minus t. Right? And okay. So actually we need to combine this. We need to use another trick here again because sine, let's change the color. So actually sine x minus, sorry, sine y is equal to 2 times cosine x plus y over 2 times sine x minus y over 2. Right? You can plug in this here, and you will get, this is nothing but 2 cosine. So you can identify x and y. So x plus y is t, omega 0 t, and sine x minus y over 2 is sine omega t, capital T. This is small t, this is capital T. Okay. So now we can take the limit of whole expressions finally. So here we have omega 0 t. Now we have cosine we have omega 0 t times cosine omega 0 small t minus these two will be cancelled. So here we have minus cosine omega 0 small t sine omega 0 capital T, right? And then you can factor out this cosine omega 0 small t, and you take the limit of this take the limit of this t to plus infinity. Because t is infinity and this is sine omega t is always smaller or equal to 1. So actually it's something like this. 1 minus x, 1 minus sine x over x. Right? And this is just equal to 1. So actually the limit of this thing is 1. So finally we know the velocity autocorrelation functions is nothing but this is proportional to this cosine of t. Okay. Good. And now the next thing is we need to perform the Fourier transform of this VAF of t. So this is simple because we already know the answer of this cosine. The Fourier transform of this cosine will just give you 1/2 delta omega minus omega 0 plus 1/2 delta omega plus omega 0. So this is the final answer. So if you plot this velocity the Fourier transform of this velocity autocorrelation functions, so you will get the peak around plus or minus omega 0, which tell you the intrinsic oscillation frequency of this timer, right? But actually, this Fourier transform of this velocity autocorrelation functions, you can say something more about this. This is proportional to the density of state of this density of state. Maybe you are not familiar. So actually, this will related to the spectrums of the molecule. So actually, I have provided you a Python script to calculate uh, the Fourier transform of the velocity autocorrelation functions with different for this molecule for the for the hydrogen chloride and with the potential in using the Morse potentials. So actually, then let's have a look. Some examples here. I will also provide you the code. Share here. So actually, I have already provided you the Python script for calculating the velocity, the Fourier transform of the velocity autocorrelation functions in the harmonic potentials and also the Morse potential. And here we have several different uh, case. For instance, here the first picture is correspond to uh, the potentials which is in the harmonic approximations, so they are almost the same. And now you can also add some damping, so this peak will smoothen out. And you can also have a different case like in a in a weak enharmonic, so which means your oscillation range is very large. So you can see the peak will be separate between the harmonic approximations and also the Morse potentials. So the peak position will also shift. And in strong and harmonic, you can see we have two peak being separate here in the Morse potential. And now the last one is the case for the dissociations. The harmonic approximation is still here, but now there's no frequency here because it's already dissociated, so the frequency is very small. Is either very small or it's very large, so you cannot see anything here. So I hope this will give you how can this velocity autocorrelation function spectrums can be useful to understand the intrinsic property of your molecule. And finally, I would like to thank you for your attention and thank you very much.